Okay, hi everyone. Welcome to the next episode of Quant Club. I'm going to be talking about basically continuing the notebook that I had worked on last time, looking at some interesting things you can do with tree methods, trying to use what you can learn from them in sort of new or different ways than just making predictions. Um, and I just want to check everyone can see this notebook. Please let me know if you can't. Um, But just to review a second, we were basically trying to extract like embeddings from trees. Basically, you can use the trees as the trees you learn from like a gradient boosting thing as a sort of way to learn a different nonlinear representation of your data, and then you can use that for other things. And so it sort of showed you can basically make it as like a preprocessor for a linear model and it's sort of equivalent to the full model. But then once you have this embedding, these weights you get on the leaves, you can do things like shrinkage to them in sort of this linear regression type way and potentially get some improved performance. So I want to revisit a couple things I said. So if like here's a plot of that I showed last time of basically leaf weights and then having shrinkage applied. And for example, I showed that you could potentially get a higher Sharpe ratio using shrinkage. And I looked at this a little bit after I showed this last time. And one thing I didn't mention, but this function, this score by date, has the functionality to do is look at correlation in the top bottom. And when I actually looked at the correlation in the top bottom after shrinkage, it looked actually worse. And that's yeah, I mean that kind of thing can happen where things can look good across the whole data set, but then when you just look at the tails, things can actually look worse. And so I thought about just playing with the shrinkage a little bit. So rather than this shrinkage I applied up here is basically just shrinking all of the leaf weights towards zero in a sort of equal amount. This is sort of like an L1 type penalty. And people had mentioned in comments and things after, they're like, oh, you could just do some of these things just with regularization terms in XGBoost. And yeah, that's true. But doing this sort of post hoc way gives you some more flexibility. And you can see that actually might be important here because that actually doesn't seem to work that well. But if you do something like shrink to the third power. So what this is going to do, you take your leaf value, take it to the third power, and then shrink it based on that. Basically, very high leaf weights are going to be shrunk a lot, and very small leaf weights are going to get shrunk hardly at all. And you can see the before and after of that. So the before is in blue, and then after the shrinkage, you can see that these very high leaf weights get shrunk a lot, where a lot of the smaller ones aren't shrunk at all. And you can think that that might be a good thing to do for some of the reasons I mentioned before. A leaf weight that has very few instances in it is much more likely to have a very high weight, but it may be less predictive because it's based on a much smaller amount of data. And again, please, if anyone has any questions, please stop and interrupt and ask a question. So these potentially very overfit leaf weights are regularized a lot, where these other ones are not as much at all. And when you apply this kind of shrinkage, you can see that the predictions you get out are sort of much more similar to the original ones. You can see that the scatter plot using this sort of uniform shrinkage. It's obviously very highly correlated, but you get a much bigger change across a lot of points. With this sort of more focused shrinkage, they're much more correlated before and after, except for this sort of region of points which correspond to these high leaf weights, which are changed much more. But you can see after doing this type of shrinkage, the top bottom scores actually, both Sharpe and mean actually look a little bit better. And so by shrinking this way, which you couldn't actually do using the parameters of like XGBoost, because this sort of nonlinear shrinkage isn't really supported. you can actually get some improved performance on both on the top bottom score as well. I also mentioned you can sort of directly use like the number of points in each. And I had proposed using like the square root of the number of points. You could also, let's see, so you could, instead of just using the square root, if you just use the 1 over the number of points as your shrinkage, and then even like square that, so you're very aggressively shrinking things that have a very small number of points. And then if you apply that, you can see where if you actually do it not just based on the leaf size, but you're shrinking based on how many points are in each leaf, and shrinking based on that, you see this phenomenon where, again, you're shrinking these very high leaf weights, even though you're doing it based on the number of points in there. And again, you actually see in the top bottom performance better performance than mean and sharp, which was not the case before. The top bottom performance for sharp was actually a bit worse when you were just shrinking without being so aggressive about the number of data points. So yeah, it's always good to check both just sort of standard correlation and also look at the tails. The tails are obviously very important to us for building portfolios, and so I hope somebody had tried this method and actually noticed it worked worse in the tails and maybe come up with ways to fix that. I was just sort of showing things I'd come up with to try to fix the tail performance that seemed pretty successful. But now let's move on a bit to some of the more interesting things I wanted to talk about. Someone had mentioned in the comments interesting ways of using the sort of representation you learned from weights, because I was sort of showing this sort of feature encoding you get out of the leaf weights is sort of equivalent to, and then putting weights on that with linear model is basically just equivalent to the tree model. Someone had mentioned you could take the sort of embedding these feature weights from the trees and feed that to a neural network, which sounds like a great idea. You basically have this really good embedding learned from trees, and then you're fitting actually a nonlinear model after that. Yeah, that seems like a great pre-processing framework, and you get some of the benefits of both tree methods and neural networks that way. What I'm going to be doing here is a bit different. I'm just going to be fitting a linear model, but I'm going to be fitting a linear model for each era. So I'm just right here, I'm just importing ridge regression. So just making and just setting a fairly high regularization parameter. And then I'm just going through each era and fitting a model from this embedding learned from the trees. And the embedding is learned across the whole data set. So it's the same set of leaf weights, the same sort of embedding is being used everywhere in the data set, but we're fitting a separate set of linear weights from this nonlinear embedding for each era. And I'll get to why you might want to do that in a second, but right here, we're just looping through the eras and fitting a linear model in each one. And so basically, just collect all the coefficients from all the linear models and then just normalize them. And this is just looking at a scatter plot of the coefficients in one era versus the coefficients in the next era. And you can see that they're somewhat correlated from era to era, but they clearly change a lot. What is actually what is very tricky about the Numerai problem is this sort of, it's not just that the input distribution can change, it's that the sort of functional relationship between your features and your target can change over time. And that's what we're going to try to get in this. And if you just try to do sort of embeddings on the features, and that if you just do it like an embedding on the features, that doesn't sort of necessarily get you how the functional relationship changes. And so sort of standard distributional shifts methods don't necessarily work that well. So what we're going to try to do here is we learn a sort of nonlinear mapping in each era, because we're sort of have this nonlinear embedding and then just a linear mapping. And so because we have a sort of linear mapping, just a set of weights for each era, we can look at how the weights change over time. and then maybe try to extrapolate how the weights might look in the future. So so you basically are trying to find a nonlinear model in this sort of linearized way that maybe works better at a future time point. But to do that, you're just going to basically collect all these coefficients and perform an embedding. So I'm just using UMAP right here, which is a great package similar to TSNE, that has a few more parameters for flexibility. And then we're going to just learn like a 3-dimensional embedding. So basically we just this is just using 15 neighbors, just a hyperparameter. Here we're just passing in the coefficients to learn the embedding. And I am going to color each point by the era number. And so here's a scatter plot, just a 2D projection of this 3D embedding. What you can sort of see because of the color map is that in this embedding, you can see that the weights basically change in this sort of continuous fashion from one era to the next. You can basically this is creating sort of a 3-dimensional space, and the sort of weights on these nonlinear embeddings are sort of going through this sort of interesting, weird path in this 3-dimensional space. Does that make sense to everybody? Please ask questions if you have any. Okay. So yeah, so this is sort of like a latent space of the relationship between features and the target. And the best solution is sort of moving it through this 3-dimensional space. So the idea is basically we want to predict into the future. We might want to sort of look at where we are in this embedding space and then try to extrapolate a little bit into the future. So like in the latest era, we are it's ending like right around here. So the idea is basically, can we take where we are in this embedding space and then just sort of project a few eras into the future, and then now we have like a new place in embedding space, and then we can sort of try to invert that and go back from this embedding space to the weights and use those weights with our embedding and try to use that to predict at that point in the future. So you're basically trying to create a model that should extrapolating from where you are in this sort of latent space should work better at this point in the future. That's this sort of general idea. So to do that, you have to find some way to kind of extrapolate from where you are in this embedding space. And I tried some like fancy like RNN type things, and none of that like worked that well. So what I ended up doing instead was basically just like a Taylor series extrapolation. And the Taylor series is basically just using like the first and second derivative to basically approximate a point plus a step. And so you just basically use your first and second derivative to approximate a little bit away in the function. And so I just basically use this Taylor series idea as a way to extrapolate where you are in this place. And so what this looks like, if you take this embedding and are basically projecting 5 points into the future, and that's essentially what this looks like. So these are just 3 different 2D plots of this 3D embedding. And you can see that based on the first and second derivatives, we are projecting that the future places in this embedding space are these red points. And you can see that looks like a pretty reasonable thing just based on where these yellow points, where it's going here, and then just predicting the future. From this angle, you can see it's sort of this curve continues along there, and it sort of continues along there. This sort of Taylor series based extrapolation, to my eyes, looked better than anything else I was able to come up with for trying to extrapolate in the future. It just sort of looks like the sort of natural extrapolation of a human would draw if you were to try to continue this line in latent space. And so then the question is, can you invert from going from this latent space back to the weights that you need to plug into your model to get a prediction? And so UMAP actually does have a way to invert the embeddings. I found that they didn't really work very well at all for reasons I'm not completely sure of. But when I tried using just these standard inversion methods that come with UMAP, the answers didn't make a lot of sense. And so I found it worked a bit better to try to build your own sort of inversion from the latent space. And the way I tried that was basically to use like kernel ridge regression. So kernel ridge regression is basically a kernelized version of like linear regression. So it allows you to learn nonlinear relationships. And so what you're going to try to do is learn a nonlinear relationship that goes from a point in your embedding space back to the weights, back to the coefficients that you fed into it. And that's all this is doing. This is just, and this is doing it for essentially one coefficient at a time. So you're learning a ridge regression model separately for each leaf weight, for each coefficient. And so, yeah, so that's, you're looping over the coefficients, and I'm using for this a cubic radial basis function. So this is just right here, just computing a distance matrix in embedding space, and then this is just computing a cubic radial basis function kernel. And then you can just use kernel ridge regression imported from scikit-learn, and then fit a model to go from this your kernel matrix to the coefficients, to each coefficient. And so, yeah, so you are basically learning a whole bunch of a bunch of little models to invert this transform. And yeah, so the idea is basically once you have this set of models, you can basically take a point in embedding space and have it try to spit out all of the leaf weights for the future. So this is just looping over all the models and getting your predicted weights at a different point in the future. And so, yeah, this is basically just looking at how correlated the inversions are to like the last coefficient. So if you actually look at the last point in your let's see, what am I doing here? Yeah, basically I was just doing some sanity checks to see if the coefficients and this sort of inverted embeddings actually look like they're approximately the same. And this is just doing a few scatter plots here to check that. Yeah, I went through this all very quickly. I hope people have some questions to talk about regarding this. Please, anyone.
Yeah, MDO. I was wondering, did you have a chance to like evaluate how that looks? I was even thinking for that extrapolation part, you could like kind of check at times in the past, right? You could extrapolate and then like see how close that was to like, where those embeddings actually ended up, like in the UMAP picture.
Yeah. So
does that even make sense? Like to compare, like say you did have the data for those red dots, right? Like where would those real red dots would have ended up, like in that picture, right? I don't know.
So I mean, you can sort of check. Well, so I mean, yeah, you learn a model that goes from essentially each of these points back to parameter space, back to the sort of weight or leaf space.
Right.
And yeah, and if you check to see how well that inversion works, it actually works quite well. And just sort of due to how kernels work, sort of nearby points should work pretty well. The question is like how well, how far away from this sort of learned inversion function does it continue to work pretty well? But yeah, basically for the points you learned these methods, like you've learned this inversion, it works pretty well. But yeah, I think what you're saying is like once you've been inverted, that if you tried to go back, where would it go to in this space? I mean, it should be pretty close to where it looks like in here, but yeah.
Yeah, or like if you had cut it off earlier, right? Extrapolate it out and then like, even just look at the embedded location or the inverted location back in the high dimensional space. How close was it from reality, I guess. Just kind of like
Oh yeah, yeah, I see what you're saying.
like using like the history of what's actually there to check like how close this is to really working,
Yeah, no, yeah, I hear you. Yeah, I haven't really done much evaluation on this yet. This was more just sort of like a proof of concept. I mean, the answer sort of depends on, you can see in this sort of latent space, sometimes things continue on in sort of a fairly linear trajectory for a while, or sort of a nice curve, but then sometimes abruptly change direction.
Right.
And so, yeah, I mean, some of these abrupt changes in direction are going to be like, if in real life this did not sort of extrapolate in the same sort of way, if it abruptly decided to change direction, obviously the extrapolation would be not right. And
but at the same time, there are lots of sections that do continue on pretty smoothly for a while, right? So
yeah, exactly.
You might be right, for quite a while, like 80% of the time, right? But then it like around those sharp turns, it would be like incorrect, I guess.
Yeah, exactly. And it's important to note, so I did 5 points into the future, sort of because like if you were doing this, you would basically want to be fitting this on the data that is available up to the latest era you have, because then you'd basically be trying to predict 5 eras into the future, which would be like the current live data.
Right. Okay.
And so yeah, you can see that the obviously this last point, this like 5th point of the extrapolation is clearly the most error prone, because you're sort of like the furthest along your extrapolation.
Yeah.
But yeah, you can see that in like a lot of places, 5 points into the future like sort of continues on very nicely, but sometimes it changes direction. So yeah, I mean, it's so yeah, it's one of these things that like could work like a lot of the time pretty well, and sometimes might fail catastrophically. The question is like, how catastrophic is it if it goes off over here? Is it like, is the solution you get even that much worse than just sort of like using a model that worked well in everywhere? Because still you're in a pretty different part of the latent space over here than you are like on this other, like on the other side of things. Even if you're like fairly, if this like actually went over here or something, you're still fairly close with your extrapolation here than using like all these other places. So yeah, you still might have a like decent solution because you're still sort of in a more reasonable place in this sort of latent space than yeah, I haven't done much to actually try to evaluate this yet. I kind of wanted to put this out there and have people play with it and see what they can build with it.
Cool. Do we have the notebook somewhere available?
Yeah, I put up the sort of first half of this notebook it's on a GitHub people can look at. I'll put up the second half soon after this as well.
Cool.
Someone asked, in Slido, you said the tree-based models could benefit from being trained in error batches, just like in a like this. Let's see. Yeah, basically someone was pointing out that there's there's a pull request or an open issue on LightGBM on trying to control how samples are used in bagging. It's not exactly what I meant. What I sort of meant is something Tim is actually working on right now, which is trying to use error information in determining how splits are made. And the idea being that you want a split for a tree node to basically work well across arrows, not just across data points. And so trying to use like sort of arrow-wise statistics to determine how splits are made. And yeah, it sort of relates to some of these out of distribution learning, where you're basically trying to learn models that work in a different variety of environments. And a lot of that type of work is very applicable in the Numerai data set, because each arrow is basically like a different environment, and you're trying to learn a model that works consistently across environments. Well, yeah, please let me know if you guys have tried any of these ideas about using like embeddings learned from trees as input to neural network or other type of models. If you have any success with any of these sort of shrinkage techniques, if you've actually played with some of these ideas for trying to learn a latent space from the mapping from these, trying to learn a latent space basically from these linear weights. The reason I like that sort of way to learn a sort of latent spaces. Latent spaces are kind of hard to learn from like nonlinear models, and so doing it in the learning linear weights on this nonlinear transform allows you to have the sort of same nonlinear transform across all the eras, and then just to have different weights for each era. So you can actually learn a latent space across eras. If you just did like a linear regression from just sort of standard features to targets in each era, you could probably learn something as well, but just it's a much less powerful model because you're sort of stuck in just this sort of linear regression from features to targets. But once you make your features these tree embeddings, you have the benefit of having a much more powerful representation that's this sort of nonlinear tree-based representation that we know works quite well. And so you're learning and embedding in a much richer and much more meaningful space. And so it hopefully works quite a bit better. And yeah, trying to do this with like neural networks could potentially be tricky. I mean, you could potentially try to have some sort of like autoencoder type thing where you project everything down to like a three node layer. You're sort of compressing everything, so it has to be within these 3 nodes. And you may learn some sort of trajectory type thing like this, but you also might not. It might just sort of learn some sort of weird clustering thing, and it might not have the sort of like nice continuous pattern that you see when doing it this way. I was actually somewhat shocked at how well this kind of worked, how sort of continuous these lines are. It's a little bit sensitive to the hyperparameters you choose, but not actually that much. I found the sort of most important thing for making it work pretty well was basically just normalizing the coefficients. So basically, after just fitting this linear model, just z-scoring all your coefficients was all that was really necessary for it to give you this sort of nice continuous embedding. And yeah, that's and normalizing the coefficients is a totally reasonable thing to do. Because like it won't really change the correlation of your predictions from the model, normalizing the coefficients like this. It's just to make sure they're all on sort of the same relative scale and sort of more comparable from one error to the next.
Andy, I've got a question for you quickly. Do you think there might be any interesting insight gleaned from the magnitude of the move in between eras on the embedding?
I do, yeah. I mean, I think there's I'm like, I would think it's very likely that sort of like sharp turns and sort of more turbulent moves through embedding space are when things are basically behaving more like more differently than they usually do. It's sort of like when the markets are kind of like more volatile and more thrashing, and just like the relationship between features and returns or targets is changing a lot very quickly. So yeah, I would suspect that sort of these longer continuous stretches are sort of more like periods of tranquility, where some of these more like sharp turns and stuff are like when there's large market moves that are sort of harder to predict.
At the same time, would the top left there, for example, looks like maybe there's some fairly large jumps in between eras, whereas at like 4-6, there's quite a few points which are quite close together.
Right here.
Yeah.
Yeah, I mean, this is partially that you might have to look at this from another projection.
Yeah.
This is a 3D embedding. You can let's see if we can try to tease out. So I think that's basically right here in this other projection. So it is like it's basically like this kind of sharp turn that looked at from another angle. They look like they're all on top of each other. Does that make sense? Is that what you're seeing?
Yeah, it makes sense.
And yeah, there's no reason you need to necessarily like limit yourself to like a 3-dimensional embedding. I mean, you could potentially do higher dimensional embedding and still do like this Taylor series extrapolation in higher dimensions. It should work just as well, and might be a much richer embedding. It just, yeah, 3 dimensions seem to, I mean, is at least good for visualization. You don't need that many things to sort of visualize a full space. And yeah, and there's also, I mean, there's also potentially like other kernels you can use. This is just a kernel that seemed to work pretty well for this kind of problem. This is not a sort of standard kernel that's that's available in scikit-learn, but it's sort of it's a kernel that has some like sort of nice properties of invariance and whatnot. But yeah, other kernels could work. Like I found Laplacian kernels worked okay. Gaussian kernels didn't seem to work quite as well. But yeah, just for learning that's inversion, there's a lot of things to play around with as well.
I've got another question, which is, so this is basically using projecting forward from weights from recent history.
Yep.
But yeah, I guess not trying to glean any information on what the weights should be from information in the current era, right?
No, it is this extrapolation. So like this. Oh, let's see. Yeah, from the current era, like you don't. There's not much to really know about the weights in the current era. All you have is like the weights. This sort of like last yellow dot is the sort of last information you have, the sort of last relationship between features and targets. And so you're just trying to extrapolate the relationship of features and targets, which are the weights, into the future.
Yeah, I guess I was just trying to suggest that there might be some other way of trying to glean information from just
from the distribution of the
exactly. So like the joint distributions of features.
Yeah. Yeah, potentially. I mean, you could potentially somehow try to tie a feature, just pure feature embedding to this. Maybe there's something you could do to see if you can try to help extrapolate better. Yeah, that it sounds potentially possible. Yeah, I've always been struck by like how how the feature distribution, how shifts in the feature distribution haven't seemed like that meaningful, and just sort of like the sort of shifts in the relationship between features and targets that um, is what really matters. Like feature distributions are kind of, I mean, we do so much normalization and pre-processing on the features. Their distributions are kind of weird already, and then looking for shifts in that, I've never been able to have much luck with that, but maybe other people do. Does that make sense?
Yeah, makes sense.
Wiggle Muse, I think I see you there, Andy. Do you have any questions?
I see you want my long-winded help to get a conversation going, but do you hear me? I think I turned it on. Okay. I don't really. I do find this interesting. This stuff you did this week is a little bit over my head, but the stuff you were doing last time is nothing I've done myself, so I don't have a lot of questions until I really get into it. But there is some stuff there that I hadn't thought of, so I appreciate that, but I don't like have enough teeth in the experience of it to really know what to ask at this point, other than to go, that's something I can work with.
Sure. Yeah.
One thing you were just talking about that I've done, and I don't know the value of it or not, but it seems to work better than I would have thought. Normally, you take the data and you make some models based on the historical data, and then predict on the future data. So that's the normal way of doing it. And if you make an embedding, like if you change the data in some way, then same deal. But I was playing around and I thought, because I make a lot of these models that are sort of instance based, or like nearest neighbor stuff, or stuff that can be created very quickly. And I thought, I could actually take this week's live data, or today's live data as we do it now, and it doesn't work if you don't change the data, because it has to have an embedding. And so what I do is take the live data and then alter it in some way. So let's say simple example, you do PCA on it. And then you would take all of your historical errors that you're going to use to predict and do PCA on them based on today's live era. And then instantly train all of those models. So the downside is you can't do anything complicated, because you need to train a model or a series of models into an ensemble instantly right before you predict. So my models, of course, take forever, but they can't take, very long at all. So I don't know if that makes sense. In other words, let's say you're doing PCA normally. You would do PCA on your old era or whatever, or just a single PCA globally, and then you would convert that, based on that formula for the live data, and then you predict. So what I'm doing is I'm making the embedding from the live data and then moving everything from history to that, rather than the other way around, which is what you usually do. And then instantly creating models, very fast created models, which could just be non-models like instant-based or very quick trees or something like that. And then instantly predicting, and then you just throw away all your models because they're only good for today. And then so I'm comparing, and you can see why that wouldn't work if you don't change the data, because you have nothing to bring the history, it's all the same stuff. So it only works if you alter it in some way, and I do it with like PCA, or I use diffusion maps and some other things, a kernel, stuff like that. And anyway, so I've been comparing these two versions, the sort of straightforward way where you and the ones that I make based on the live data have been kind of beating the other ones by enough that I've noticed. I'm like, so that's actually pretty interesting. But again, it does have a lot of downsides. So I don't know if that's related to what you were just talking about, but if you can pour your entire pipeline into today in an hour, or I'm mostly predicting for tomorrow because I can't do any of this in an hour, but I could do it in a few hours.
No, that's an interesting idea. It's something I hadn't really thought about before, because yeah, I mean, basically the to sort of restate what you're saying is you by doing PCA like on the most recent era, you're sort of finding the feature, like how features vary the most recently, and then sort of using that set of basis vectors and transforming all your past data to only caring about the sort of past data variation in the ways that the current era has lots of variation. And then you so you're basically making the models focus on those directions of variation.
So I'm changing the entire historical set,
exactly.
Keeping the same historical targets, instantly training a bunch of models on that newly altered historical data, and then instantly predicting, and then throwing it all away because as soon as you're done, it's not useful anymore. So
that's, I mean, that's
it's also a lot different. I mean, I just wanted to see, I figured, it wouldn't be, because in the first way, I do everything in big ensembles. So I'm doing like, 1,000 eras or several hundred eras, and I do them all separately. So if I do PCA, I'm just using PCA example, that doesn't work the best, but I might do, 300 eras, and I PCA them all individually. And then when I do the prediction, I actually convert the live era 300 different times to make the ensemble. So I'm not making one single global embedding that I think is the best. I just make a bunch of them. So in the reverse case, you are only making one embedding and then converting everything to that. And I just wanted to see how different they were. And they're obviously correlated, the results that you get, but they're not as correlated as you would think. And then stuff like PCA, where it's very fast and very simple, you can actually do a combination of both ways. You can just mix the whole thing together and do PCA and that. In other words, you can mix the historical live era, or the live era and the historical era into one big era, do a PCA on that joint era to get some sort of bizarre middle ground, and then make all your models instantly again. So again, this is pretty unique to me, because I don't think most people are going to make all their models the second they use them and throw them away.
No,
you can't do a lot of.
I think it is interesting and does make some sense to me, because you're basically it's like making all your historical models try to focus in on the sort of directions and variation and features that are relevant today. And
I will say also that I'm getting murdered right now. So maybe you shouldn't listen to anything I say, but those ones are doing a little better than the other ones. So there might be a sort of a survival recency bias in there or whatever, but that helps in weird cases like this. I'm actually not getting murdered globally, but I'm getting murdered globally, but I'm not getting murdered on all of my models. Some are doing good, some are doing bad, but the bad ones are just killing me and I need to purge. So it's not like everything I'm doing is crap, but some of it obviously is.
No, it seems like there's always going to be, using techniques like this, like you mentioned, and like the one I'm mentioning here, you're kind of trying to sort of tailor your model to where you think the world is right now. You're trying to basically get the best predictions based on what you think the sort of state of the world is at the current time, rather than just sort of using the average across all the previous measured states of the world. And doing that, it seems like, yeah, like sometimes it's going to be a lot better and sometimes it could be a lot worse. It definitely, it seems like a much more high variance strategy, rather because like, yeah, because like, so, I mean, your guess about the sort of state of the world, if you're right, your models are going to be way better. And if you're wrong, they could be way worse than just using the sort of average across everything, because the average is probably closer to what it actually ends up being. But yeah, it's with this sort of embedding thing that I'm proposing, it's possible that even if you're like fairly wrong in how you extrapolate, you still might be in a better place in latent space than the average. It's sort of an empirical question. Because yeah, it's like how it doesn't look like you can get that far off in 5 steps most of the time. Like you can see, even when the things have a pretty sharp turn, it's not like they move to the other side of the embedding space over 5 arrows. So it's still, you still might get actually a fairly decent solution. But yeah, it's I do think there's you can clearly do a lot better potentially if you get the sort of state of the world, what the relevant features, the relevant mappings.
Yeah, well, that's the entire game, really. So guess the world, right? If you could do that. I don't like just relying on recency bias as a main strategy. It's just contrary to my detriment at times. I think it's just contrary to my philosophies. But what I do, is sort of both ways. I'm sort of trying to take the state of the, I don't know, the shape of the variables or whatever, but still mapping all the historical data with the historical targets into that space, so it just fits a little better, maybe.
No,
anyways,
yeah,
that does kind of work. It's time consuming, but
yeah. Yeah, and because you're still training on the past, and yeah, this method I'm proposing is a kind of combination of recency and history, because like the embedding that I learned, the tree was basically learned over the whole data set. And this sort of embedding is really just sort of changing the relative weights of these things that were learned over the whole data set. And so the feature set should be a generally good feature set always, because it was learned over the whole data set, but you're sort of rebalancing it on a per arrow basis and sort of looking at how that rebalance changes over time. So I think it's definitely really bad to go too recency bias, like just training your model on the last like 10 arrows. It's clearly a bad idea and not going to work very well.
Yeah, well, it does work. It works too often. That's why it's tempting.
Yeah.
So. But there it goes very badly sometimes.
Exactly. Yeah. Yeah. As you say, it can work for a while, and you can get like lucky for a while, but it can go very horribly wrong. And so, yeah, these sort of methods, like what you were talking about and what I'm describing here, are, I think, decent ways to try to bring more recent information into it, but still try to use information from the past, try to use models from the past to inform your predictions.
And that's the other big goal with sort of synthetic data, is if we can make fake data that isn't just a different copy of what we've got, and somehow project or fill out areas of the feature space that didn't happen, but fill them in with something synthetic that is plausible for what would have happened. Is that just impossible, or?
It's not necessarily impossible. I mean, one way you could, with what I'm describing, one way you could sort of make fake data is, because this is sort of all just in the parameter in the sort of mapping space. What you could do is you could just sort of sample random points throughout this latent space, and get so that basically corresponds to a mapping from features to targets. You could basically use that mapping at different places at different eras. So you could basically use the sort of same features, but have it create a new target based on this embedding. So basically, just get the predictions from the any given era using some place in this embedding space, turn that into a target for that era. So you're basically as a way to sort of make alternative universe targets for the same sort of input data. So you're not making sort of resampling the features, you're sort of resampling the feature to target mapping. And then that's a way of making synthetic data. Because basically we'd be training your models to work well across many potential mappings from features to targets.
Mm-hmm. I know some people have tried to, take the live era and compare it to, historical eras and find the best ones that would be, most applicable to today. And every time I've tried anything like that, where I'm trying to pick and choose sort of blind, but based on some reason, it's always been horrible. It never.
Yeah,
but I know some people do that. I don't know if they have a lot of luck with it.
I've tried that. I've tried that as well a long time ago, and yeah, it would sometimes seem to work okay, and other times work horribly wrong. The reason I sort of figured out, I mean, that the reason that made sense to me why that didn't work is because the eras that have the sort of same feature distributions don't necessarily have the same feature to target mappings. And so, yeah, even if the era looks sort of similarly in a feature way, because you're usually just basing these based on the
you have to, right? Because there's no target.
You have to, all you have is the features. But if the target mappings are very different, if the sort of functional relationship between features and targets is very different in those eras, it's definitely not going to help you. And that's what I was sort of that's why I sort of came to this sort of method where you're actually trying to map in this sort of like functional relationship way. We're actually trying to basically find similar eras in this sort of functional relationship, and it looks like the most similar era to in terms of functional relationship to any given era are the eras just right next to it. Which is
and that's the other problem. As soon as I see that when you try to pick an era, you always just end up with the adjacent eras.
Yep.
Then I'm like, well, okay, that's boring, and that's just gonna it's gonna work until it doesn't. So
yeah, exactly. And so that's why I mean, you essentially you have the problem is as I try to formulate here, it's just like an extrapolation in some latent space. So you're trying to basically use the most recent eras mappings and try to end in the sort of trajectory in the space to try to project forward to see what that mapping might be in the future.
But at the same time, we see that history doesn't ever really repeat itself, right? Because it'd be nice if you just saw like a circle go, an orbit or something. But yeah.
Well, the problem in markets compared to, weather or anything cyclical is that, or maybe not weather, but is that it's always reacting against its own history. So you're pretty much guaranteed to get that sort of effect. Whereas, that's why trends never, just keep going, because they reverse because everyone, either gets on them or starts to bet against them or whatever. So you can always count on a new weird twist to something.
For sure.
And
but yeah, it's interesting. You can see that there's within the structure of this embedding, there's even kind of like a larger scale structure. You can see like the more recent points are like to the left overall, and the older points are toward the right. And so there is like this kind of like very like local, very curvy structure that is more wild, but on maybe like a larger scale time structure, things are more similar. Things evolve maybe more slowly. You can sort of see that here as well. So yeah, there's clearly interesting structure on various timescales within markets, but yeah, it's clearly not cyclical or anything easy like that. Cool. I think we need to wrap it up now. Thanks everyone. Please give feedback on Discord and ask any questions. I'm happy to answer anything. I'll be putting up this notebook very soon, same place as the other one. Just check Discord for the links. Thanks everyone for coming, and thanks for the questions, and hope to see you guys next time.